I think the pressure's on. Once you can start to collect data properly, the pressure's on to get as much as you can. At the moment, we've been looking at calibrations, and there's not a lot you can do about that. That's not something that we're specialised in doing, so we've just had to wait and let them get on with it. But once we get a green light, we'll be measuring this system for the next 2 days or so. You just work through the night, so I think we'll just be taking it in shifts, drinking a lot of coffee. We bought loads of Krispy Kreme donuts as well, so we'll be eating plenty of those. I've got 5 kids, so I'm used to not sleeping particularly long periods of time, but I think we'll work in shifts around the clock because it's really important. This is an extension of the videos that we've had before that explain how nanoparticles form. This is the reactor that we use. It's a hydrothermal reactor. We know that it works and we can collect products, but what we don't know is actually really what's happening on the inside. So this is a familiar bit where the two fluids come together, hot, cold, particles form. We don't know what's actually happening around the inside the reactor. So if you put X-rays through the reactor at high energy, you can actually take measurements of particles forming. I don't think it's blue in real life, but those particles can be actually measured as they form around the tip of the nozzle reactor. It was a concept. We had no idea what we would be measuring or how the data would come out or whether we could do it at all. So yeah, this is a conceptual thing. We're actually sat in a control room in Diamond, which is exactly where we want to be, so that we can fire those X-rays straight through a reactor. We've set it up and we've spent a day making various tests and so on, so we're ready to go. Okay, this is the hutch, and so it's all lead lined because the X-rays go straight through that pipe, through there, and we've set up our reactor in the way. So, I mean, effectively the beam comes through here, through this tiny slit, straight through that steel, and out the other side to a detector, and it gives information about how the particles form, how the precursors transform into nanoparticle crystals. You're only allowed to come for very short periods of time, so we're here for 4 days, and they literally lock you in. So we've been here for more than a day so far, and we're feeling pretty tired. But you have 4 days to make as many experiments as you can, and they teach you all the safety training and all the basics about what you're doing. But essentially, then they'll leave you to do your experiments. So far, we've been at this for about a day and a half. We have had a little bit of sleep. They do allow you to do that. So we're working in shifts as of now to get as much data out as we can. It's difficult, and we've spent a day trying different techniques which have been sort of successful, but not quite what we wanted. And today we're trying something new. So it is difficult, and you have to be very patient. But the best thing is the people that work here are geniuses. They really are. They know their stuff. We wouldn't be able to be in here if it was switched on. And there's all sorts of very, very important safety things that we go through in training and so on. But the beam is actually coming through here. The X-ray beam is coming straight through here, through various sort of slits, and from there goes straight through the reactor and out the other side through another set of slits and then onto the detector, which is that half horseshoe thing on that side. So that's actually going to collect all the information, and that is fed back directly to the control room. So we actually get online measurements of what we're doing, and everything's fully automated, so we can make changes in here, changes in the control room. That happens here, and then the detection information then comes straight back to us. We know what we're doing in the reactor, and we know the products that we collect, but what we don't know is the changes that take place around the tip of the reactor or just downstream. So being able to measure those changes tells us an awful lot about what we can and can't do with a system. So we might be able to develop new materials, which will be very exciting. It enables us to understand why certain materials like titanium behave differently from other materials, say like hydroxyapatite. Why do they form the way that they do? Some form shaped needle shapes, some form crystals, round crystals. Some will form very crystalline materials, others are amorphous or rutile and anatase and so on. If we understand why they do that, it means that we can maybe predict other materials or how to change the reactor so that we can make particularly specialized materials. We can infer what's happening, but sampling inside that reactor as things are changing would be almost impossible. So this beamline enables us to take measurements as they happen inside very difficult materials to penetrate or to see inside. I think it's a bit like an Olympic village for nerds, but it is very exciting. I'll be more excited, except I'm so tired. So I'll be able to rest when we're finished. But right now, we're just trying to collect as much data as we can in as short a space as we can. When we're actually looking inside the reactor, the X-ray beam goes straight through the center of the reactor and outside to a camera on the other side. But obviously what it was doing is the electrons, the X-rays were actually going through the safety screen. It's making marks on it, so it doesn't heat it up a lot, but it's actually sort of effectively etching the surface of the Lexan. We were working out if we did a certain scan pattern, we could draw a smiley face.